And we just finished talking about oxygen nucleophiles. We first talked about water as a nucleophile to aldehydes and ketones to form a hydrate. And then we went on to talk about the reaction of aldehydes and ketones with alcohols. And so remember, alcohols can react 2 times with an aldehyde or ketone. It reacts once through an addition reaction to give a hemiacetal, and then it reacts a second time to form the acetal. So we kind of went through this long mechanism to convert the carbonyl to the hemiacetal and onto the acetal. And remember that the main things we want to do with that, other than just memorizing the whole thing, is to try to understand what's going on, right? From the beginning, we have to, because we have a weak nucleophile, we have to protonate on the carbonyl to make the carbonyl more reactive. Once we've done that, then the alcohol can act as a nucleophile, right, to form a tetrahedral intermediate, and then we essentially have acid-base chemistry in the middle. We get to the hemiacetal, and then we just look at which group we need to remove, either the OH, if we're going toward the acetal, or the O alkyl if we want to go back to the carbonyl. Okay, and we do that by protonating, right? Whatever we need to make into a good leaving group, we protonate it, and then it can come off. Okay, so there's a lot of individual steps that are similar to what we've seen before. All right, so the last reaction that we're going to look at is something quite different, and this is referred to as this is German. It's not Wittig, but it's called the Wittig reaction. All right. And I remember when I first learned this reaction so many years ago that I was kind of thrown for a loop because all of a sudden the reagent has a phosphorus in it. And I was like, oh, what do I do with phosphorus? But now I'm more comfortable with that. Okay, so we're going to learn the Wittig reaction, then we're going to do a few synthesis examples, trying to mix all this up together. And if we have time, we're going to start into Chapter 22. So what Chapter 22 does is look at carboxylic acids and their derivatives. And again, we're going to look at mostly some weaker nucleophiles. And they are going to do predominantly this nucleophilic acyl substitution reactions. So we've seen these reactions already with strong nucleophiles, but now we're going to do them with weaker nucleophiles. Okay? Any questions? All right, let's do a clicker. Okay, so we've done a lot of these already. So we've just got what's called the Wittig reaction. Okay, so in this reaction, here's what the overall transformation is going to be. And we'll see that it can do more than just this, but in fact what we're going to do is go from this aldehyde, or we could do it with a ketone. And what's going to happen is that this oxygen of the ketone is going to get replaced with a carbon. All right, so we're going to go from an aldehyde or a ketone to an alkene. All right, pretty tricky, huh? All right, so the reagent that we're going to use to do this is going to look like this. It has a phosphorus, and instead of drawing all of these out, I'm going to say that pH equals phenyl, Okay, so what's a phenyl group? It's like a benzene ring, right? Equals a benzene ring. So I don't want to have to draw those out because they're just going to get carried through. So I'm going to say P with 3 phenyl groups around the phosphorus. And then we're going to have a double bond here and a CH2 like this. Okay? So this species here also has another resonance form that we can actually use to help us understand the reactivity here. And the way that this works is that because phosphorus is, anybody remember, is there a periodic table in here? No? You remember where phosphorus is in the periodic table? It's right underneath what? Nitrogen. Okay? So it's lower on the periodic table than carbon, though it's one position to the right. But it's more electropositive than carbon is, because it's on the second row. And so the resonance here is like this, with more minus charge on the carbon. So the resonance form would look like this, with a CH2 here and a plus on the phosphorus and a minus on the carbon. Okay, so this type of species that has a minus and a plus adjacent to each other has a weird name. It's written out like this, and it's called an ylide. Okay, and so what we can see here is that because the carbon has the minus charge, it's going to be more the nucleophilic end of this ylide. All right, so the way that this works then, if we aren't just drawing that resonance, and I kind of covered up all my space here, is I'm going to make another arrow and this bond, or we could draw it from the minus charge if we drew that resonance form from down there, is going to attack the carbonyl carbon. But this first step of the reaction is a concerted step. So in essence, the one reaction that we've seen that's more like this step is the hydroboration oxidation. Except this is actually going to form an intermediate. Let's draw the intermediate up here that has a 4-membered ring in it. Okay, so here's the cyclohexane. Here's the oxygen is now attached directly to the phosphorus. And this goes to the CH2 group. And this has an H down here because we had an aldehyde. Okay, so we form this 4-membered ring. It's called an oxyphosphatane. All right, now what's kind of cool is this, sometimes we call this a 2+2 cycloaddition. So we have 2 pi electrons on one side, 2 pi electrons on the other side, and we form a ring. It's kind of like the Diels-Alder, right? But the Diels-Alder is 4+2 because it had a diene on one side, so 4 pi electrons combining with 2 pi electrons on the other. Okay? And so this cyclizes to here, but then look at how we get to our product. So it cyclizes with 2 arrows like that. The ring comes back apart with 2 arrows that look like just the reverse, but it essentially goes together one way and then it opens up the other way. And if we do that, we get this alkene plus this compound here. It's a H, and this is tri-, phosphine oxide. And that phosphorus-oxygen bond is very strong, and so that's kind of what the driving force is to make this very stable, very strong phosphorus-oxygen bond. Okay, so those two come together, 2 plus 2 this way, and then they do kind of a reversion. It goes backwards, but it goes the other way. So it transfers the oxygen to the phosphorus and connects the 2 carbons together in a double bond. All right? So how do we make these ylides then? Okay, so the ylide is up in the middle there. So right here, right? This is the ylide. And so we're going to make those from alkyl halides. And there's 2 steps to doing this. The first is the reaction of triphenylphosphine with the alkyl halide. And because phosphorus is just below nitrogen in the periodic table, it has the same type of electronic structure, though because it's in the 3rd row, it can have this kind of expanded octet. It can have more than 8 electrons around it. But it has a non-bonding pair of electrons, and so it can use those just like nitrogen would. And so what it's going to do is essentially an SN2 substitution with the alkyl halide. Okay, so what we're going to get then is we're going to get this methyl group, in this case, connected to the triphenylphosphine. The triphenylphosphine was neutral to start out with. We've added another bond, and so just like nitrogen, when it had 4 bonds here, it's going to have a plus charge. And we have a bromide as the counterion. So we've made a salt, first off. It's called methyl triphenylphosphine bromide. Phosphonium bromide. All right, so we're not quite to the ylide yet. So if we look at this salt and we look at the ylide that I drew up at the top, what do you see that we have to accomplish to make the ylide? Just look at the formula. Look at how many atoms there are. What do we have to do? We have to remove a proton. Exactly right. Okay, so we're going to have to treat this with a strong base. Okay, most commonly for this kind of ylide here, we're going to use butyl lithium. This is an extremely strong base. Okay, just an alkyl lithium. And this is one of the common ones, and so you can actually buy alkyl or butyl lithium in a jar, as a solution, as a standard solution. But you got to handle it with syringes and everything like I've described to you before. All right, so this is going to, here I'm going to make a small change here. I'm going to put I'm just going to put 1 hydrogen up here so I can deal with this. So this is going to come over to here, and this is going to go down like this. Or we could just put the electrons right on that carbon. It just depends on which resonance form we want to draw. All right, this would have its resonance form. I know it's kind of messy up there. It would look like this, and a minus. Okay, so this is the ylide, this is the nucleophile. All right, we can make these ylides with various species, not only just with a CH2 on the end. Here's one we're going to use a bromobutane, and so then we'd form first our salt that would look like this, plus, bromide is minus. We'd add our butyl lithium. Sometimes you'll see butyl lithium like this with just a Bu for butyl. And that will remove one of these protons on the position adjacent to the phosphorus to form this ylide. Okay, so we can add more than just a CH2. We're going to make an alkene in each case, but that alkene can have, more carbons attached to it. All right, we can even do one down here. This is with benzyl bromide. So this would do the same thing. We'd form the salt. Treat that with butyl lithium. And we make the ylide. Like this. Okay? So now in each case, what's going to happen when we react these ylides with the aldehyde or ketone, it's going to be this whole portion, or this whole portion. These are going to essentially replace the oxygen of the aldehyde or ketone. Okay, so that's how we can get to our product. Okay, so let's think about, we're going to start with a product here, and we're going to try to decide what aldehyde or ketone and what ylide we could use to synthesize that alkene. Big of a question?
So for the ylide, are both resonance structures considered the ylide?
Yes. Anytime we have resonance, right? It's just the true structure is a composite of all of the resonance structures. Yep. Okay, so the way that we're going to work backwards here is what we know is we're going to form this bond. We're going to form the alkene. All right, and so we're just going to split that apart. Okay, and I'm going to draw this like a retrosynthesis. And so I'm going to just make this. I'm going to make our double bond there. We just broke that double bond. And I'm going to make this double bond over here. And on one of these, I'm going to put an oxygen. So let's just choose one. I'm going to put an oxygen, say here. And on the other side, I'm going to put the phosphorus and the 3 phenyl groups. Okay, so that's where we can get to one starting point. All right, so is there another way that I could have done that? Yeah, I could have switched them the other way around, right? All I did was break that double bond and pull it apart. I just chose to put the oxygen on the left one. I could have put the oxygen on the right piece. So let's try that and see what we get. Okay, so here I'm going to make this same piece. And then over here, I'm going to make this same piece again. This time, I'm going to put the oxygen on the left, on the right. So this would give us an aldehyde then, and the phosphorus and the 3 phenyl groups will go on the left piece. Okay, so at least in theory, I could make this molecule using a Wittig reaction in 2 different ways. Okay? And both of those might work. There is one that is a little better if we have to decide between we have to choose between 2 equivalent possibilities. And the one that's better doesn't so much depend upon which one does the actual Wittig reaction itself, but it has to do with the formation and the synthesis of the ylide. All right, so remember that the first step of forming that ylide is the reaction of triphenylphosphine with the alkyl halide. And I described that as an SN2 substitution, right? So if we look at the two ylides here, let's draw them over here, and we think about the alkyl halide and the triphenylphosphine that we need to use to synthesize these. All right, from this one, we would start out with, oops, I did that wrong, with triphenylphosphine plus, say, a bromide, a halide here, like that. Okay? This is just the first step of it, right? And so this would be an SN2 substitution. And then we'd get the salt, and then we'd have to treat that with butyllithium. Okay, what would we go backwards? Let's see if I gotta fit it in way over here. No, that's not the right one, is it? I already did that. Okay, so now I want to go over here. Okay, what would we form that ylide from? Okay, so then, can you guys see that green all right, or is it too light, or is it visible? Okay. Okay, so then the carbon where the phosphorus is attached would start out, say, being a bromide plus the triphenylphosphine, right? And that first step would be an SN2 substitution like this. All right? So is there one of those SN2 substitutions that looks better to you than the other? Which one, the top one or the bottom one? Who think the top one? Who thinks the bottom one looks better? Oh, it's about 5-4. Way to put it on the line there. Okay, well, if we're thinking SN2, what's one of the main things about SN2? If we look at that reaction, they both have the same nucleophile. What's more reactive for SN2? A primary alkyl halide or a secondary alkyl halide? Primary, right? SN2 favors less steric strain, right? So methyl is best, primary is best, secondary works sometimes, tertiary doesn't do SN2, all right? So if we have to choose between these two, this would be better, okay? Because we're using an SN2 substitution between the triphenylphosphine and the primary alkyl halide. Okay, so that means that this is the better way to go if we have a choice. Okay? All right, so let's look at the bottom reaction. So see if you can draw out the product for that bottom reaction. So we already have the ylide, right? We don't have to synthesize it here. Given the ylide plus our aldehyde. So is there just one possible product, or do you have to make a decision when you draw that product? What kind of decision? This, yeah, the stereochemistry, right? It says it right there. All right, so if we draw these out, right, so we're going to make a double bond. We know that we're going to essentially combine the phosphorus and the oxygen, and we're going to connect this carbon to this carbon right here. All right, so if we want to draw this out, we can draw it like this. So there's 1, 2, 3, 4, 5. That's for the aldehyde on the left. 1, 2, 3, 4, 5. And we have 1, 2, 3, 4 carbons on the right, so we could go 1, 2, 3, 4. So this would be one possibility. The other possibility would be like this. Okay, we could form either the trans or the cis or the Z or the E, whichever way, isomers. Okay? We might get a mixture of those two. The book says that the trans is favored, but that is not correct. What's favored with these types of ylides here is that the cis is favored. And the trans is less favored. Okay? Going to get a mixture, but we'll get more of the cis than we get the trans. I've done quite a few of these reactions before. Okay? There is a way that they don't tell you in the book, but I'm going to show you because you really want to know now how to make the trans, right? So I'll just show you kind of this isn't maybe the best one, but it's the closest to do this, so we can keep it in a fairly narrow group here. So we're not going to go to the same products, but we're going to go to an ylide like this. Okay, and if we use this one, then we'll get products like this. We can get trans. And we could get cis. But in this case, it's the trans that's favored. Okay, so the difference here is that the ylide that I drew at the bottom is what we call a stabilized ylide. And so why would it be stabilized? Can you see anything about the structure that would stabilize it? Resonance, right? So look at the ylide double bond is conjugated with the carbonyl. Okay? And we could even understand this even further if we drew, that's not what I did. A resonance form, that the normal resonance form of the ylide would be like this. Which would have the electrons here and a plus on the phosphorus. Okay? And so now look at the minus, that non-bonding pair of electrons is next to the carbonyl. So in fact, we can draw additional resonance. I'll just draw the arrows and not the actual resonance structure, but we could draw them to be shared with the oxygen of the ester. All right, so there's more resonance in this ylide, so this one is stabilized. The upper one is unstabilized. Okay, because there's no further conjugation to help stabilize that. And so the main difference kind of fits back to some things that we've seen before. So the top one, because it's not stabilized, that anion of the ylide is going to be much more basic. Okay? And so it's going to add irreversibly And when it does that, for various reasons, it adds, and it has to twist around to form that four-membered ring and stuff. So we won't draw all that. But kinetically controlled conditions with the unstabilized ylide leads to the cis product. Okay? When we stabilize it, the ylide is much less basic, and so it's a better leaving group. And so it can go on, it can come back off, and the reaction becomes reversible. And so then, when the reaction is reversible, that leads to thermodynamic control. And the trans double bond is more stable. Okay? So stabilized ylides tend to give trans double bonds. Unstabilized ones favor cis double bonds. Okay, and it all fits in. You know, we've seen the kinetic control and thermodynamic control in other situations. Okay? All right, so this is the Wittig reaction that in a synthesis example, but I'm going to make a small change to my structure here. I'm going to make this, instead of an aldehyde, I'm going to make it into an ester. So our starting point is an ester. So what do we have to do? Let's look. We want to compare the reactant to the product and just see what's been accomplished, right? And so if we count, let's say we count from just the alcohol, the closest alcohol here. I'm just going to count from here. 1, 2, 3. We count from that same alcohol. 1, 2, 3. And so we see that this position right here with the arrow used to be the ester carbonyl. Okay? And what we need to do is extend it, forming a double bond, trans double bond with this new ester out here. Okay? So how can we do that? Let's just move back. Let's do retrosynthesis. How could we do that? Well, you could look back at this reaction that I just told you about. I know that wasn't long enough to sink in yet. The stabilized ylide, right? And if we did that, I'm going to draw all of this in here. Then we would be doing the reaction of an aldehyde at this position with, oops, this is the H, our stabilized ylide. This is the ester right here, right? That's a shortcut for an ester. And that's really looks too sloppy. Okay? So that would be the reaction that could give us that double bond. All right? And then what about going from an ester to an aldehyde? The dibal. So it's a reduction reaction. Remember that we can use dibal, diisobutyl aluminum hydride, followed by water, and that reduces an ester one time to give us an aldehyde. And it won't go further than that. Okay, so here's kind of what we have to do to change the part of the molecule that actually changes. All right, but do we have any problems with the synthesis? Okay, what's the problem? With the alcohols. There's those two alcohols, for one thing, reacting those with dibal. Dibal is very basic. It's going to just deprotonate those alcohols, and it's going to kind of quench our dibal. Same with the ylide. The ylide is basic as well. It would just react with the alcohols. All right? So, what do we have to do to those alcohols? We have to protect them. So we could do this in two different ways. All right? We could do it the way that we learned before. All right? And how did we learn how to protect alcohols before? The silyl ether. Okay? So we could use, we just use chloro with the silicon, and we are just going to use R3. Okay, and I think we used, not two. They also had a base in there, and that was imidazole. Remember imidazole, we talked about the basicity of those two nitrogens one time. All right, so if we used enough trialkyl silyl chloride, we could silate both of those alcohols. Okay, so we would get R3 silicon, so we get these silyl ethers. All right, and so now those are protected, and so we can do the chemistry we need to. All right, so we do our dibal, followed by water. Basic conditions don't affect the silyl ethers. And this will go to the aldehyde. Okay, then we're going to react this aldehyde with this ylide right there that I already drew. And we're going to do the Wittig reaction. Okay, so then we get R3. Fit this in again. Okay, the double bond there, and here's our ester now. Okay, and then we have to remove the silyl groups. All right, anybody remember how to do that? It was the fluoride, yeah, N-butyl, tetrabutyl ammonium fluoride. So I'm going to draw, well, I think they used this abbreviation, tetrabutyl ammonium fluoride. Okay, so this is essentially F minus. Okay, and that reacts with sulfur, cleaves those bonds to release the alcohols, to deprotect the alcohols. Okay? Now, I'm going to show you another tricky way to protect those alcohols using chemistry that we learned just in this chapter. Okay? So here, I'm going to do this. I'm going to react this with acetone and a weak acid. Okay, so you tell me what that's going to give us. Okay, so we have, what functional group did we mostly learn about in this last chapter? Ketones and aldehydes, right? And what we have is now a reaction of, we just added a ketone to this, acetone, and we have alcohols on our reactant. Okay, so those alcohols can react with the ketone. In fact, there's two of them, right? So what if we, I can't really cover this up, but what if you just thought about, if you broke the bond where I wrote 1 and 2 there, if you just ignore the rest of the molecule where the ester is, and we just have a 1,3-diol, and it reacts with a ketone. You remember that reaction the other day? Yeah, so we're going to form a cyclic acetal. Okay? And we used a cyclic acetal as a protecting group before, but before we had a ketone that we were trying to protect, and we used a diol to protect it. Now we have a diol we want to protect, and we're going to use a ketone to protect it. Right? So we're going to reverse the roles here. And so what we're going to get, I'm just going to twist that one oxygen down like this, and this one down like this, and here's our acetal. And this is still our ester. Okay, so we've made this cyclic acetal, right? But this time we're using it to protect the diol. Okay? So now, I'm not going to do all the rest here. I'm going to do a couple of arrows here, and then we could get to after our Wittig, right? And then how would we deprotect? We just need to hydrolyze it. So we want to use water under acidic conditions. Okay, so then we just use water and acid, and we hydrolyze the acetal, and we get our product. All right. Okay, so we're almost out of time this chapter right now. Here were just a couple of other fun synthesis problems. Yeah, question?
Sorry, there's a reaction in the book where it uses silver oxide that selectively...
Silver oxide, usually to selectively oxidize alcohols to aldehyde. It's called the Tollens. Well, silver oxide, silver nitrate.
So the one in the book is, it's where it will basically react, but it won't react with the alcohol, so it's not going to protect it.
Mm-hmm.
Just react with the other compounds.
Yeah, let's talk about that afterwards, yeah. Okay, so go ahead and take a look at these. What I'm going to do when I get back to my office, I'm just going to fill in some ideas on these syntheses, and those will be on the notes and on the video. And then tomorrow morning we'll start in on chapter 22. All right? So I'll see you guys tomorrow. Here are a couple of additional synthesis problems that we didn't get a chance to do in class. So in the first one, what we want to do is convert benzene into this compound here, where we have this alkene attached to the benzene ring. So if we think about this in the retrosynthetic way, up until today, the only way that we had to synthesize alkenes was through elimination reactions. So we could, in theory, try to do an elimination from a halogen like this, or we could try to do a dehydration from an alcohol like this, but both of these have a problem to try to get to that less substituted alkene, right? Because both of these, if they were going to eliminate, would follow Zaitsev's rule and they would yield to the more highly substituted alkene. All right, so neither of these are actually very good ways to synthesize this compound. So a good way to do it has to do with using the Wittig reaction that we talked about today. So the Wittig reaction allows us to go back to, instead of an alcohol or a halide, we can go back to a ketone, right? And that ketone, we saw this one in class essentially today. We could use this ylide that just has a CH2 group on here, and that would just add the CH2 up on top. And then of course this ketone, this acyl group attached to the benzene ring, we can easily make by how, you remember, we can do just a Friedel-Crafts acylation. Okay, that does that in one step. There would be other ways to get to that. The ketone, we could brominate the benzene ring, make a Grignard, and react that with an aldehyde, but that would give an alcohol, which we would have to oxidize up to that ketone. So the Friedel-Crafts is definitely the way to go. So we can do this conversion just in two steps. The Friedel-Crafts alkylation followed by the Wittig reaction. Now, if we want to carry on further from there, right, now we have an alkene that we can do all kinds of alkene chemistry on. So let's see if we can convert that product from the top one here into this compound over here. Right, so the first thing always to do in synthesis is to try to figure out which carbons correspond to which when we compare the structures. So what I would probably do is consider this ethyl group, this part of the molecule, as being the same as this. Okay, so what that says is that it's really this CH2 group here that we have to convert into this other double bond. So we have to extend it by one carbon, and we have to move the double bond out to the end. Alright, so I'm going to do this just in the synthetic way. So if we want to modify that end carbon, a good way to do that would be to put a bromine or an alcohol out on that position. So I think here probably the easiest way to do this is to do a hydroboration oxidation reaction. Remember, and that does the kind of anti-Markovnikov hydration reaction. So we added a new H there and an OH out at the less substituted position. If we then oxidize that alcohol to an aldehyde, okay, I'm going to do that, and I'm also going to rotate around this bond right here just to line it up with our product up there. There's the ethyl, and now we have an aldehyde at this position. Now we can do the same Wittig reaction that we did up above. And it's going to replace that oxygen of the aldehyde with a CH2 group and forming that alkene. Alright, so these are just a couple more examples. Tomorrow we'll start in with chapter
22.